So we have our first presentation, an IoT-based smart irrigation management system with real-time notification. And the speaker will be Mehendi Hassan. Okay, well, thank you very much and welcome to this meeting. Well, go ahead. Thank you very much.
Hello, good evening, and from my side, it's midnight, and hope everyone are doing well. First of all, thank you, conference chair and session chair for facilitating a wonderful presentation session. And my name is MD Mehdi Hassan, and I am from Bangladesh. And my presentation title be an IoT-based smart irrigation management system with real-time monitoring and notification. Basically, Bangladesh is heavily relies on agriculture, and most of these people are dependent on agriculture as to cultivate food. And around in an every years, around 37.266% produce crops. Seasonally, it's an season around yearly two. And this current irrigation system use 35% water for producing 1 kilo of rice. And in Bangladesh, around 84% people live in rural areas, and those people are totally engaged on agriculture, and their contribution in our national economy is around 62%, whose are labor forces. And our main objective of this research is to build a smart irrigation management system and to reliable and easy monitoring system, and as well as then reducing complexity of existing systems, and it can be happen and cost effective because most of these people are in Bangladesh are not affordable in costly irrigation system, and that's why we can be focused on this issue. And this is the some of this previous research where we can be comparison show this which part of this improvement we can be done in this research. So first of all, Bangladesh is an riverine country. Around 54 rivers are flowing across the countries, which are is 230 two-third of our total land. And in this we can be and it is always dependent on hidden seas, hide and tide, and that's why this canal water monitoring is an important issue in our in Bangladesh. And as well as and it can be pumping water, and some of these research can do it, and some are also be tools. And some of these research are can be detect soil moisture. Some are also we can haven't detected rainwater, as well as in daylight sunlight monitoring. It can be day or night. And one another important advancement in this research is then use in long distance data transmission, though using LoRa. And some of these previous research are also we haven't focused on website. Some of them have an mobile app and notification like SMS, LCD, and email, and all those uh, advancement we can be done in this research. And our system having two part. One is transmitter part and another is receiver part. In transmitter part, there are the operation are accumulated with an Arduino Pro Mini, and there is also we have an LCD monitor, LDR, asynchronous water level sensor, soil moisture sensor, humidity sensor, and relay for controlling water pump switching, and as well as an rain sensor, and for SMS notification using GSM. And another part there are also we have an receiving for the using LoRa. LoRa and it can be accumulated with an ESP32 microcontroller. And this is the system overflow for transmitter part. In transmitter part, all those sensors have an threshold value to accumulate to which part this operation or pumping and can be start or off, and all those parameters can be checking gradually, and there is a having two decision. One is motor on and another is motor off. And in other part there is also an receiver part operation where all those data are stored in data server using ESP32 and receiving by LoRa. And this is the system receiving transmitter and receiver circuit diagram. And this is this is our prototype, and one of this prototype and another prototype will also be implemented in field, and where we can be show that all those sensors are also be available there. And there are so many visual visual representation here for this monitoring all those data. For on-site LCDs can be gradually monitor all those data, and we are building in mobile app, and it can be monitored soil all those data using gradually. And there are also we have an website we can build though using Node.js, Next.js, and CSS. And there are also we have an database MySQL for storing a large amount of data. And there we have in this part there are also have an email notification. And this is the data visualization for different sensors whenever it can be active. And in conclusion, and it's an real-time monitoring system, and it can be easily accessible though website, mobile app, and email for long distance. And in future it can be have an integrated to machine learning for predicting large amount of data analysis easily. And there will also be have an implementation of renewable sources for sustainability. And references, and thank you. Any question?
Thank you very much for your presentation. I would like, is there any questions that you'd like to make? Any of you? Please go ahead. I would like to ask, this you want to make reproduce this development. How many you think in doing? It's a prototype. You're going to do many of them, or what is the idea behind for this Arduino type based system?
Okay. First of all, we are also using two part. One is the prototype, and another is the implementation large scale. And currently, we are working in large scale, and all those data are also be found in large scale. And for this presentation purpose, we also be just showing prototype.
And why? The communication that you're doing a lot. Is this correct? A long range communication device in the system.
Yeah.
Why is this? Is it very? It would be in the. It's an agricultural device, so it's long in what sense? 1 kilometer, or it's meters? Why it has to be long range?
Okay. LoRa can approximately cover 12 kilometer, but in practical it can be cover 10 kilometer.
Okay, so that's the reason. And so this system, it will be connecting also to smartphones, or it communicates with a server, and that server is communicated with the wireless. I don't know if you have
Yeah,
If
yeah,
you
yeah.
put that in your
Yeah.
presentation, if you can
Okay.
show us.
Okay, okay, okay. In receiver part, there is also we have a data server to storage large amount data, and gradually it can be monitored though using mobile phone as well as an website. Yes, we can build this at our website though using Next.js, Node.js, CSS, and also we have a large amount of data storage for MySQL database.
Thank you. I don't know, if, does anybody have a remark or a question for this presentation? Okay, okay, thank you very much. So I think we can continue to the other presentation. You'll be doing the next presentation, I guess?
Just I have a minute, need one a minute.
Okay. Es Héctor Atleli Romero Pando. Él lo va a hacer presencial o it's going to be, he's going to talk here or he's going to be online. Is any of these other speakers here that will be presenting? You- Which one is it? It's, it's the last one?
No, después de esta, ya.
Cesar Morales?
Sí.
Okay. Precision underwater navigation. Okay. Okay, the next one. Diego López? No. Saúl Córdoba? Mhm, okay. So I guess the other ones will be online.
Diego López sí está en línea, está conectado.
Okay, Diego López. Okay, Diego López Hernández. Okay. Héctor Atl. María Diego. Sí, Atl también.
También están nada más. Queremos a las.
Así es, Chacho.
Hello. Sorry for that. Okay.
Okay. Can you turn on the mic?
Okay. Is it
Okay,
clear?
yeah. Yes, we can hear you again. So we will begin with the second presentation. It's an industrial centralized control automation system using an IoT-based embedded system. The speaker is Mehdi Hassan. Thank you very much, and go ahead, please.
Okay. Again, thank you, Converse Shell. My presentation title will be Industrial Central Automation Control Monitoring System using IoT and Embedded System. And I am from Bangladesh and International Islamic University, Chittagong. And in Bangladesh, there are also we have an garments manufacturer country, and it is currently world's second largest garments manufacturer. And in our country, there is over the last 3 decades, from 1992 to 2020, 237 facilities fatal incident occurs across 4560 Bangladeshi garments factories, and most of in 94% are also be causes for fire, and 3.38% for boiler explosion, and 1.27% for building collapse, and as well as 1.27% for other factors. And this casualties around those timeline is 6870, where injuries are where 500 181 death, and 1689 are also we have an injuries. The highest toll occurs between 2011 to 2015, where 38,000 people are injured, and as well as 12,087 lost their lives. And for those assessment, we are also we haven't focused on this research to environmental friendly industrial automation system for overall focused on garments workers as well as in factory, to increase in factories safety. And our main objective is to have an low cost industrial central automation system building, and as well as to increase safety, and it can be have an easily monitor, and it can be reduce the existence complexity, and as well as cost effective. And this those are previous research comparison, where some of these precaution measures are also we have an some of them have an LCD, SMS, Bazaar, or mail, mobile app or website. Some have been focused on fire detection, temperature control, detection, and as well as in water sparking whenever fire incidents can be get. And some are also we haven't focused on detection gas, and most of these mm, factories doesn't have an for exhaust fan cooling system, and this is the main root cause for Bangladesh to have an incident some of this incident irregularly, and currently it can be improved. And most one of these industrial load control is another big issues for our factory, for factories, because some of this factory doesn't care about this issues, and it have an good risk assessment for further all those accident gradually. And there is also having in our system there is also having manual and as well as a touch sensor for this operation run on and off to switching. And this is the system block diagram where Arduino Nano can be accumulated those this prototype all the sensors to measures, and there will also be having receivers where ESP32 can have an and receive those uh, data, and storage is in a data server. And this system can be having an assessment those this is input values, and it can be having some of these sensor are also have an analog sensor, and in the triggers it can be having converted to digital signal for longer fast sensor. And some of and though the data communication are also using HTTPS communication protocol for secure communication for protecting an external threat. And in receiving part, there is also have an receiver doing data communication, and it can be having storage data server. And this is the system circuit diagram, uh, and this is the prototype where we can be built, and all those sensors are also be having, there is also be having fire sensor, optical sensor, motion buzzer, and sensor relays and exhaust fan. And load we are also be using for load for prototype using light as to monitoring those issues. And there is also be having DC motor for fire sparking. And there is also in receiving part uh, node MCU and one GSM are also be used for on-site data availabilities and SMS communication. And this is the visual representation, and here website can be having monitor all those data by month and by weekend. And this is the mobile view where all those parameter inside this factories can be measured. And this is the visual representation comparison of time wise. In it can be a start 8 a.m. to 5 p.m. And there is also be having fire flame sensors data, however it can be having accessible lows that can be having measure those is in certain parameters. In visual representation, there is also having an LCD for email notification and SMS notification, and it can be having real-time monitoring and accessible though website, mobile app, and as well as an email. In further research will be cooperating with and machine learning. Thank you.
Okay, well, thank you very much for your presentation. So now we have time for questions or remarks. I don't know if somebody wants to ask a question.
Yes.
Yes, go ahead.
I have a question. The device that you design, where does it have to go in the factory? Because I mean, the gas concentrations are not the same everywhere. So have you made a study to choose the best location for the device, or right now, where are you locating it?
Okay, it's basically we are also be currently we are working in a factory for implementation, and for real-time experience it can be having around 15 or 60 meter upward set, and it can be easily capturing those orders data easily. Yeah.
Okay. Thanks.
Somebody else, other questions? So I have a question. So you're making tests, field tests
Yeah. Currently, we are also working in field test in a factory.
Okay. And how does this type of systems relate to, I guess there's industrial commercial systems. Why develop these type of systems? what
Okay, basically,
advantages?
basically, in Bangladesh, most of this industrial system doesn't have any security purpose, security safety systems, and it can be in real time. There will also be having PLC control. As you know, PLC control system have a high price. In one PLC module have an around 2 or 3,000 USD, and there's high level of costing. But whenever we can be switched in Arduino or ESP32, and currently ESP32 we are also be working it, and ESP32 is 10 times faster than Arduino, you know, and it can be have an accessible though is in real time.
And another question would be, so it's for I guess it's more for small type factories, or
Yeah,
and you
can
can integrate a
okay,
number of nodes, whatever
okay,
type of nodes you
okay.
like, or
Okay. Currently, we are also working in shoe factories, and it basically it be small factories, and we are also be working to monitoring and analyzing this data. And further, we are also be thinking that some of these additional suggestions also be there, and it can be having further research.
okay, thank you very much. So, would there be any other questions or remarks?
Yes.
Yeah, we have another
In
question.
the table,
Okay.
you showed that the proposal device is better than other strategies to detect the risk. Why is do you use more sensors, or you use more computational equipment? Why do you do why your device is better than other strategies?
Okay. Am I right? It can be, you can be questioning why this all those uses some of this additional sensor in conventional. Generally, we can use a conventional sensor. Am I right? This question. Okay.
Can you repeat, please?
If we could you repeat again? Because I don't.
Uh,
Okay.
about the it's a comparison between your your device and other devices, other strategies. Do you use more sensors than other devices to detect more scenarios? Maybe.
Okay. First of all, we can have a comparison table. Am I right? With there. Yes, it can be like this. This is the comparing tables of existing system in different papers. It's done around last 3 years or 4 years research around the world, and we can be also analyzing which um, um, protection system are also be available in those work, and how we can be input or to advancement in our work. And there will also be having some of this analysis is one important analysis we can be done here industrial load control facility system, because in currently we can work we can be monitor that current industries doesn't care about this load, because they can be having without background connection with this new load, and they can be and not properly assessment those kind of how many load they have and need, and they can be is it riskful or is it reliable for their factories. And we can be also be having check this issues in our research to assessment the further assessment for fire incident, or as well as another precaution measures.
Okay, well, thank you very much. Then, well, I think if there's no more questions, then we would like to thank the speaker for your presentation, and shall continue to the next talk. Thank you very much,
Thank you. Thank you.
Hadi.
Thank you. Good day.
So the next presentation will be also an online presentation. Um, in behalf, it's Hector Atel Romero. Can you hear us? And can you please turn on your camera? We can't hear you. I think your mic's off.
Okay, hello, can you hear me now?
Yes, we can hear you.
Okay, hello
Okay,
everyone.
well,
Hello,
thank you very much. So we will continue with the next speaker. So it's the talk is entitled Optimal Risk Sensitive and PID Control Applied to an Actuated Pendulum. The speaker is Hector Atel Romero Pando. So
Thank you.
so we have normally 15 minutes, but we're the other presentations were shorter, so it could be 15, 20 minutes, and then we can have 5 minutes of questions. So we'll
Okay,
go ahead, Hector, please.
okay, I'm going to share my screen. So, I think now. Okay, I guess my screen is visible now.
Yes, it is visible.
Okay, I'm going to begin. Hello everyone, my name is Hector Carlos Romero Pando, and I'm going to present the conference titled Optimal Risk Sensitive and PID Controls Applied to an Actuated Pendulum. This work is carried out in collaboration with Universidad Autónoma de Nuevo León and Universidad Juárez del Estado de Durango. We are going to introduce the following content, so we are going to begin with introductions. So first, the pendulum. The pendulum is a didactic tool that is used for teaching physics and math models and to develop systems and mechanisms that can be controlled. The pendulum is part of those mechanisms. So our particular contribution in this work is that although we are going to obtain the control laws based on the linearized model of the pendulum, we are going to apply them and synchronize the gains to the nonlinear model of the pendulum. The nonlinear model of the pendulum is going to be simulated through the model obtained by the change of variables of the original dynamics. So we are going to compare the performance of both PID and risk-sensitive control methods through a cost function that in our case are going to be the exponential quadratic cost function, and we are going to vary this cost function with different parameters epsilon that we are going to explain further. We are going to use the cost function that includes the final time term. So the aim of this study is to verify small errors and values of the cost criterion function once the tuning is reached in both controls. So we begin using the linear quadratic Gaussian model shown here. So it's 1 divided by epsilon times logarithm of the expected value of the exponential of the epsilon times the integral from 0 to final time of the functional L with respect to time plus a functional evaluated in final time. So here L is the quadratic cost the quadratic error with a heavy matrix, the weight matrix, and the control with the weight matrix. And here's the error in final time, already evaluated in final times, also with a weight matrix. Here, H and Q are going to be equal and are based on the maximum torque we are going to apply. And here, R is the identity matrix. It's important to say that H and Q can be semi-positive definite, but R has to be strictly positive definite in order that we are going to have a control in all the trajectory. So we begin with the Rig sensitive control with a Ito stochastic differential equation. So we start with this stochastic equation that includes a functional with respect to time that in our case are going to be linear, and this is the presence of a white noise. It's important to say that this stochastic equation needs to have an initial condition and needs to be enclosed from initial time to final time. So having a linear system, here for the functional, we obtain the control law by optimizing them in the Hamilton-Jacobi-Bellman equation and solving for the optimal control that in our case is going to be U. Here this U star is going to be our optimal control, and here H represents the Hamiltonian. And so for PID control, we have a well-defined law because it's a non-optimal closed control. So we use the control given by this equation here. That is just proportional gain times the error plus integral gain times the integral of the error and the derivative gain times the derivative of the error. And so we begin with the application. So the simple pendulum, it's a classical mechanical system that exhibits periodic motion. But or the particularity of this system is that we are going to use the nonlinear model of the pendulum. And in our case, we are under the effect of a DC motor that in our case is going to introduce a torque variable that is going to be our control signal. So using the nonlinear pendulum model, in the presence of the white noise, we have the equation model given by the equation shown in 4, and introducing the state variables as state 1 as the angular displacement and state 2 as the angular speed, we plane change of variables and have the nonlinear state space model shown in 5. Here, x1 dot represents the first derivative or first time derivative of state 1, and x2 dot represents the first time derivative of state 2. So here is the state space representation of our system that we're going to use to simulate them. So linearizing around equilibrium point, we get this equation and this is the model we are going to use to obtain the control law. So here, to evaluate performance under nonlinear stochastic dynamics, we are going to implement Rig-sensitive optimal control and PID control. So we are going to compare both controls. First, we begin with Rig-sensitive optimal control. And so we, after introducing to the Hamilton-Jacobi-Bellman equation, we get this control law. This term is a gravity compensation. And so we develop a little more the maths, and we get this control vector that indicates that in the state 1 there is no control, and in state 2 this is the control that we are going to apply. So our gains we define the gains as P. Our gains are defined by this Riccati equation shown here, and P has these elements. So we solve the Riccati differential equation using numerical methods and get these asymptotic values for the gain matrix. So this is the asymptotic values for the element 1, 1. These are the asymptotic values from the 1, 2 element, and these are the asymptotic values of the element 2, 2. Because this matrix is symmetric, the element 1, 2 and the element 2, 1 are the same. So in order to converge to the asymptotic values that turn our matrix P into a positive definite according to Sylvester's criterion, we apply the transformation shown here in 10. That, as we can see, the only thing that this linear transformation does is change the signs of the main diagonal elements. So we can see here, this is the behavior of every element of the gain matrix here. The blue is element 1, 1, and green element 2, 2, and orange element 2, 1. This is before we apply our transformation, and this is after we apply our transformation. As we can see here in the zooming, and in the inset, sorry, we can see that the elements never cross 0, so it remains always positive. Now, for PID control, we initially use the Ziegler-Nichols method for tuning. So for Ziegler-Nichols, we start with a proportional gain of minus 5.438, integral minus 15.106, and for derivative gain minus 0.489. Our gains are negative because we are using the error in a non-conventional way. Conventional way is desired point minus state. We are using state minus desired point. It is not going to affect our dynamics. We just have to adjust the sign of our gains. So a subsequent manual adjustment was performed here to refine the new gains. So here we use this logic. For proportional gain, we keep the proportional gain because we have already reached our target value. For integral, we reduce the integral gain in order to decrease the ponderative effect of the error, and we increase the derivative gain in order to smooth the curve of the system. So now for results, the system was simulated in Python, and the state errors and values of the cost function and the data are summarized in the tables shown in this section. Our variable parameter is going to be our epsilon value that allows us to regulate the influence of the noise. So here are our parameters and the values we used. So for the rod length, we used 0.3. For gamma, we use 90. For mass, we use 1.5 kilograms. The gravitational acceleration is convention, 9.81 meters per second squared. We simulated in 10 seconds. For motor torque in Newton meters, 12 on peak, 4 on hold. We start from rest, so both states start in 0, and we are going to vary epsilon in every simulation. So finally, we get these results. And so for PID control, we use we get these cost values. So as we can see, the PID cost is higher than rig sensitive, but the error in state 1 is lower than in rig sensitive in state 1. While in rig sensitive, the cost is less than in PID, and the error in state 2 is lower than in PID. But in both trajectories, in both controls, the errors are so small that you can see both controls are effective, and the main difference is that the rig sensitive has a less cost values. So to illustrate this better, we have this plot. Here is the behavior of the cost function for the rig sensitive control for many values of epsilon. As we can see, the trajectories are so close to each other that you can see in the inset are so close that in the scale they remain so closer between them. So it seemed to be one single plot, but in reality there are many plots that are so close to each other. We can see here also in the plot for the error of state 1. It seems to be just one trajectory, but as we can see here in the inset, we zoom, we can see that the trajectories are enclosed approximately from minus 0.02 to 0. We can also see that as we increase the epsilon value, the dispersion of the trajectories increase. But for lower values of epsilon, the trajectories remain so close to each other. And we have the same behavior for the error in state 2. The trajectories are so close that they seem to be just one trajectory, but in reality, they are just so close to each other. And so here are the results for PID. For PID, we have same behavior. As we can see here, the dispersion of the trajectories is a little more, but it's also so small compared to the scale. For state 1, we have the same behavior. The trajectories remain close, but when we do an inset, we can see that the trajectories are enclosed between almost 0 and a little more than 0.01. And the same behavior remains that for lower values of epsilon, trajectories are so close to each other and the dispersion increase as we increase the epsilon value. And same behavior for the state 2 in PID control. So here, one of our main results is here for the control signal. Here is important because, as we can see here in the plot, the control signal of the PID control has a peak between 8 and 9, almost 8.5, 8.6, while rig sensitive control signal here is almost 4.7.8. The peak is between 4 and 5. This plot is for a fixed epsilon of 100, but the behavior remains almost the same for every control. And the lowest value of the PID signal control is almost 1.8. It's enclosed between 1 and 2, while for rig sensitive is almost 1. So what can we conclude from this? That the PID control can reach a similar performance to rig sensitive, but it requires a higher peak torque in this case, but a higher peak in the control signal, while rig sensitive can have the same performance with lower values of the control signal. So this can be traduced in a lower degradation of the system at long term. But in both cases, in almost 2 seconds, both control signals converge to a stable value between 4 and 5, that it's almost 4.5. So our conclusions are that rig-sensitive control exhibited superior performance in regulating the angular displacement, while PID control archived lower errors in the angular velocity. The exponential quadratic cost functions were similar for both controls, but only with one minimal differences, leading us to a rig sensitive is optimal, but not for a substantial quantity. And our main conclusion is that regarding the control input, the rig sensitive control reached the target state using less torque compared to the PID control. So we can see that they have almost the same behavior in every aspect we have analyzed, but in the torque, the difference is so much higher. And that's our references. And thank you for your attention.
Well, thank you very much for your presentation. So, well, the room was open for questions. If there's any questions that you would like to ask, please go ahead. Go ahead.
I have a question about the value of gamma. What happens if you change the value of the stochastic component?
Okay, if you change the value of gamma, and the gamma is shown here, it can affect the intensity of the noise. So if you increase the gamma value, the noise is going to become slower because it's dividing and it's squared. And if you turn the gamma value so low, the intensity of the noise will increase. So it's a parameter that we can use to fix how much we want to the noise influence, but not between simulations, but based on the properties of our system.
Thank you. Another question. In the you use a pendulum. A pendulum.
Yes,
Is
we are
gamma
using
is the
pendulum.
best? First pendulum. Gamma is the and gamma is equal to 90. 90 is the best value or for gamma, or the you have results or better results with another values of gamma.
We had best results with a higher value of gamma, but 90 is the lowest value we found that our controls have remained. I mean, inside of torque limits, because if we increase gamma, the influence on the noise becomes so insignificant. So when we found 90, it's the value that allows to the noise to be to influence directly in the system and to have significant influence in the system, but also letting us be inside of our torque limits. But because we are limited to the high to the peak torque and the whole torque of the system we are simulating.
Thank you.
Okay, thank you for the question. We have a question from one of the online participants, Maria Aracelia Acorta. Can you turn on your camera and please make your question? The microphone is not on.
Yes, thank you. Good afternoon. I have a question for Hector. Hector, in page 10 of your presentation, you have state the question, but I observed that you use a minus sign in the stochastic term. Yes. Can you explain me please why? Why is a minus sign in the stochastic term?
Sure. Here in the 10.
What was the question?
Yeah, can you please
Yes,
repeat the question because we
sorry.
hardly heard it.
I here in 10 and now in 11. In 11 here is the minus sign in the noise. I mean this here. Oh, here in 10. Yes. It is because the noise is not adding a signal or energy or system. It is subtracting energy. So the negative sign is because the noise is a way we introduce elements that affect our system that are not directly related to our system. So those terms are going to subtract energy, not adding energy. That's the reason why the negative sign is required in the noise.
Okay, thank you very much.
Could you repeat the question because it was not really clear? We only heard the answer. If you could speak closer to the mic, please.
Yes. My question was, why in the state equation, with the equation of the pendulum, appear a minus sign in the term of the noise? In page 11, in 11 page, appears a minus sign into the state equation as a coefficient of the noise. Why is minus or why is not more plus? I don't know which I'm blind adequate.
Um,
Okay,
Hector, can you
I think
rephrase the question?
the
Please?
question
Because-
is what I explained. I mean, I think she's asking why this minus thing is here, or in that case, why this minus here in the matrix. So
Oh,
in both
can
cases, the
you-
answer is the same because
Yeah.
the noise is subtracting energy. Here, here appears a plus, but the minus is here in the matrix, in the coefficient matrix, and here the minus is here, just in
Yes.
subtracting.
Hector, can you we don't see your presentation actually. Can you
Okay,
put it on again?
Okay. Let me see. Now you can see. No?
No, actually. Puedes ponerlo.
Actually, so let me see if maybe if I share my whole screen, it will work. Let me see.
Okay, yeah, we can see it there.
Yes.
That's okay.
Okay, here.
Just
I
leave it
mean,
like that.
I guess
Yes,
the question is why this minus sign is here, and why there's a plus sign but a minus here. And the answer is the same in both cases because the white noise is subtracting energy of our system. The white noise is a way we can include every element we are not considering or that is affecting our system that is not directly related to the dynamics. So those elements in the system are going to subtract energy. So that's why the minus sign is shown in both of these cases.
Okay, thank you very much. I don't know, is there any other questions? Go ahead.
I have a question about why did you choose to compare your control to a PID? Why didn't you choose like a energy-based control strategy, a passivity control strategy, for example, or I don't know if something more robust to the noise? Why did you choose a PID?
Oh, it is because PID controls are the most common used controls in industry. So despite there are optimal controls or robust control methods, the PID remains in top of the uses in industry. So we decided to compare our method to a more common method. So maybe someone that reads our results will be interested in changing the PID control to a rate sensitive control method. So we just comparing to the PID control method because it's almost universal used method used. So that's the reason why.
But you haven't compared it to any other energy-based control strategy.
Yeah, we could have been comparing our method to any other, and we can as long as we use the same measure tool that in our case is that is our cost function. We evaluate them under this cost function. As long as we evaluate the controls under the same cost function that in our case is the cost function, we can conclude. We can compare the controls. I mean.
Okay.
Okay, thank you very much. If there's any question, then we would like to thank the speaker for his presentation. And we
I have a question.
There's one more question.
Yes.
When one is making experiments with noise, normally one should appreciate the effect of the noise on the graphics. Maybe making a zoom, or could you please comment about this? Because the noise is is a quantity which one cannot do almost anything. Almost nothing, sorry. So
Oh,
the noise is
yes,
very should be present in your graphics.
yes, yes. It is because the our methods we are using are based on regulating the influence of the noise. So the behavior we expect is that the noise gets compensated. It can be seen
Not
here
possible.
in the result tables that the errors are in order of exponent -3, exponent -4. So here in the graphs, the scale is not enough to appreciate the influence of the noise. But if we do a better zooming, the influence of the noise is visible. Maybe we could add that graph in a future article, so it can be seen the noise directly, because in our simulations we in fact see the noise when we zoom in, but we have to zoom in some maybe at least at these scales we have here, and the
No.
influence is present, noise is present.
No, I think it's not correct. Sorry.
Oh, okay.
Thank you.
Thank you.
Okay, well, is there other questions? Okay, well, we'd like to thank you for your presentation, and we'll continue with the next talk. Thank you very much.
Thank you.
Hector. So the next presentation would be precision underwater navigation, a robust trajectory tracking for hybrid gliders via novel STA backstepping control. The speaker will be Cesar Morales. He'll be making he'll be in this room making his speech. Well, go ahead. Thank you very much.
Okay, thank you. My talk is about robot trajectory tracking for hybrid gliders via novel superficial algorithm technical. Let's start with the introduction. In recent years, the underwater technology has have been increasingly used in the fields of marine science. For instance, resource exploration, environmental monitoring, surveillance, and military applications. Such we can see here in the picture some of those applications. Now I'm going to talk about the mathematical models. Important describes the mathematical model of underwater autonomous vehicles, general vehicles of 6 degrees of freedom. In this picture, we can see the reference frames that we use to describe this mathematical model. Considering these frames, we can represent the mathematical model in the kinematics or in the body frame as given in this equation 1. But to implement the controllers, we have to represent this first expression into the inertial frame, and this expression is given in equation 2. Let's make some assumptions to the vehicle that we used, that we modelated. First, the vehicle's motion is on the x-z plane. That is, in some way, we can measure the states x, z, and theta. We assume also that the roll and yaw angles are stable. That is equal to 0. Also, we consider that our vehicle is in low speed motion, is about 2 meters per second. That implies that the Coriolis matrix is equivalent to 0, and the inertial matrix is MA is diagonal, and the last is the balance is calibrated to such that the buoyancy is neutral. Here we can see the matrices of our model, of our vehicle model. And considering that the vehicle is moving to the X-set plane, to implement the controllers, we use these two dynamics, the dynamics of set and the dynamics of theta. Without loss of generality, we assume that M1 and 2 is equal to 1. And let's go to the problem statement. The trajectory tracking control of the gliders consists of finding a control. In this case, is XG, that is the only effective control, such that the trajectory tracking error tends to 0. That is expressed in this equation 6. Yep. Here we have this diagram that represent each dynamics independently. First, I'm going to stabilize the zeta dynamics. In this case, we propose a PD controller. After that, I'm going to stabilize the zeta dynamics. In this case, we propose a super twisting algorithm controllers. This controllers is proposed controller is based on a sliding mouse. Here, recalling the equations of the zeta and theta dynamics, we can define the trajectory tracking errors as expressed here, E1, E2, E3, and E4, where F theta is part of the dynamic model. After that, we can define the trajectory tracking dynamics as expressed in equation 9, corresponding to each dynamic zeta and theta. And after that, we can propose the controllers for the zeta dynamics and for theta dynamics. For theta dynamics, we can propose a controllers like PD controllers as expressed in equation 10. In the theta and the theta dynamics, we can propose controllers as in equation 11, where the USTA is the super twisting algorithm, and F1, F2 are the compensation terms. Now I will give the idea of the stability of the whole system. Before we stabilize each system independently, but of course these systems are interconnected or are coupled. So the way to make this interconnection is by using the backstepping philosophy. Yeah, considering this relation given in the question 12, so we can rewrite like the dynamic equation of the zeta errors. And here we have a new term. This new term is arises by backstepping step. And to analyze the behavior of this dynamics, we can propose a Lyapunov function like given in the equation 14. And after carry out the derivative of this Lyapunov function, we can get this inequality given in the equation 15. And we have this term positive that is arises by the backstepping step. We have to deal with this this term. By do that, we invoke the lemma 4.7 about input state stability. After carry out some algebraic manipulation, we can find this expression given in 16. And with these conditions, with this kind of functions, we can conclude that the system 13 is input state stable. Now I'm going to analyze the stability of the theta dynamics, given these dynamics errors corresponding to theta. And with the control proposed as in equation 11, and after defining our sliding variable as in equation 18, and after a change of variable, we can propose a Lyapunov function for this super twisting algorithm as in equation 19. And after carry out the time derivative of this equation, we can find this expression in 20. And after some algebraic manipulations, we can find the expression 21, where eta is constant and C is dependent in the eigenvalues of matrices P and Q. And after, we can conclude that the origin sigma equal to 0 is globally asymptotically stable. After that, we can propose a composite Lyapunov function as given in equation 22, and the times derivative is given in 23. By invoking lemma 4.7, which says that if the system 13 with E3 as input is input state stable and the origin of the system 19 is globally asymptotically stable, then the origin of the whole system, interconnected system, is globally, the origin of the interconnected is globally asymptotically stable. Now I'm going to show some simulation. In the scenario one, we have the nominal case. In this nominal case, the robot follows trajectory trackings without any kind of disturbances. The second scenario, we applied buoyancy disturbance that affects the deep dynamics. And the third scenario is a disturbance to the affecting control input. XG is applied. First, we have here the trajectory tracking error. The trajectory tracking in dip in pitch. And we can see that the smallest values of the errors are obtained with the proposed controller. And the second scenario, we have the tracking in dip and pitch, and the smallest values of the tracking errors are obtained with the proposed PDSEA controller. Here we have the trajectory tracking errors in dip and pitch. And here we have the signal of the control input. The third scenario is we have the deep tracking and pitch tracking. Also, again, we have the smallest values with the controller proposed. We have the tracking errors, control input signal, and the conclusions. The proposed controller addresses two key challenges on the weather player vehicles. The first is managing the underreported dynamics of the system and ensuring robust performance in the presence of disturbance and modeling uncertainties. And the simulation results validated our controller, our proposed controller, and was compared with other controllers like PD and nonlinear PD, and demonstrating that the controller proposed achieves better performance. For future work, we would like to carry out some experiments in real time. So that's it. Thank you.
Thank you very much for your presentation. So, well, we're open for questions. Who wants to ask a question? Go ahead.
You mentioned in your conclusion that I don't know if you can go to the conclusion. You say that you ensure robust performance in the presence of disturbances. Can you talk more about the type of disturbance that you introduced to the model?
Yes. I'm going to the graphics. In the second scenario, we implement disturbance to the deep dynamics. We applied like a quadratic function that is acting in these parts. Here and here, you can see that.
Yes, but my question is more like in real life, what does that represent? Like a current?
Not like current. You can imagine that on the way the vehicle is navigating, and you can push like I don't know whatever to affecting the deep dynamics. So it could be represent that.
Okay.
Another question, please.
Can you show us the design of the controller? The backstepping design?
Yep. Here?
No. Oh.
Here?
No. Do you consider for the design the disturbance term in W1 and W2?
Uh,
You put that and disturbance terms.
Yeah.
One in the equation number 7 and W2 in equation number 8.
For the analysis, I could I don't consider this term.
Okay, so do you know you did them no, you don't have some characteristic of the disturbance. You don't it a disturbance is bounded or differential.
Yeah, actually, I'm not considering for the analysis, stability analysis, this perturbation term.
What kind of stability results would you have if you consider the disturbance term?
Yeah, we can. I think we can obtain local stability or to concerning this perturbation.
Local stability, asymptotical. No.
I would have to check like what kind of stability, but yeah, at this point I could ensure that we compose with kind of stability.
Another question.
Alright, then how can you ensure robust performance if you don't take into account the disturbance? I mean, practically it work, but theoretically, how can you ensure that, or you are not there yet?
Not at this time. I'm not considering these terms. I think this. Yeah, these terms could not appear here.
Okay,
Yeah.
and then just be careful.
Yeah.
With the pricing.
Yeah.
Okay, I want to have a question. As you're doing simulations and you put certain condition, how would this relate to the real implementation? Is it realistic, those assumptions in the real prototype?
Yeah. Yeah. When we make like simulations, implement this kind of disturbance, we could expect that this kind of perturbation is the same in the real experiments, and we could expect that we will have the same results. So, for example, like the gains or we are using in PD or supertensor weights will not the same in the real experiments. So we have to like retune or tune in real experiments.
Yeah, but can you put the assumptions when you for your model? It was at the beginning.
Yes.
There, that one.
Okay.
Yeah, how because no, there's other assumptions of your model.
Yes. Here.
Yes, and how that's realistic to the real implementation. Does that happen? or how close it is?
Yeah, for example, this one is could be realistic because in real time our vehicle is moving close in low speed. It's not moving in fast speed.
Okay.
Yeah. So this is the assumptions could be realistic, and this is could be realistic too because we calibrate the system that will be enough avoidance.
Okay, so the other angles that y'all, those are, you don't have any disturbances there, I guess, in your real setup. That would be a prototype, in a prototype to test a lot.
If we have like current in maybe this will not accompany.
Okay, thank you very much. Well, thank you very much. If there's another other question, we would like to thank the speaker for his presentation. Oh,
Could you please go back to your simulations and give more details because it's not very clear. It was very fast. If you are comparing with respect to what?
Okay.
Because you propose an PD as a super twisting algorithm.
Yes.
Commentary is that you should have at least put in your slides the equation of the super twisting algorithm, for instance. And it is known that the analysis is good when you have disturbances, total disturbance, for instance.
Yeah. Yes. Yeah. In the scenario one, we have the nominal case. We are comparing this PD. So PD is in the first loop, it's in the set dynamics, and the STI is applied in the second dynamics. That's why it's PD STI. And here we have we can see that the PD STI has like less overshoot. Yeah, also here in the theta tracking. But here, for example, in
What does it mean, those 2 times PD?
yeah, two times PD or two times nonlinear PD is because if you remember, we have two dynamics. And two PD means that we propose a PD in the first dynamics, not PD controller in the second dynamics. That's why it's two PD. And here, for example, we can see again that when we perform the deep dynamics, we have less error with the proposed controller. And here, when we disturb the theta dynamics, of course, we can see the results in the theta tracking. And we can see here that the controller proposed is performs better. Yeah, I don't know what else to say.
Could you please show the equation of the input? Yes, with respect to the question of the organizer of the session. Is this kind of oscillation acceptable for real-time applications? You are demanding a lot of work for your actuator.
Yeah.
Maybe it's not a good solution.
Yes.
If I have my own glider, maybe I will not allow you to use this kind of thing because you may destroy it.
Yes. Of course, when we use this kind of controllers based on slave mode, we have this kind of effects called chattering.
Is that chattering or is that
it's oscillation? No, it's not chattering. It's oscillation, but this kind of oscillations actually it could be not good for motors. But if we can see that the magnitude of this oscillation is very small, and if it's still not work, we can implement filters before this control input go to the motors.
how you can improve this?
All right.
How you can improve this?
Yeah, we can implement a filter for this control input.
Okay, thank you.
Well, thank you very much for the talk. So we'll thank you very much. We shall continue with the next talk. That is given by Diego Lopez. Can you turn on your camera, please, Diego? Okay. Can you hear us? Is mic open?
Yes. Can you hear me?
Yes, thank you very much. So the next talk will be proximal gradient-based model predictive control for obstacle avoidance in holonomic robots. Okay,
Yes.
well, thank you very much for your presentation, and well, you can begin.
Okay, thank you so much. Hello, my name is Diego Lopez, and I'll be the speaker for this presentation. Here are the topics that we'll review. Excuse me. Here are the topics that we'll review, where foundation refers to basically the theory on which the model is or the method is based on, and the control design refers to the implementation of it. First, let's talk a bit about what is model predictive control. Well, it is advanced control strategy that finds the optimal set of inputs to give to a system to have an optimal set of states throughout the whole or throughout many points in time, leading up to a prediction horizon. For example, if you're driving and you see a bump ahead in the road, well, you might say, oh, if I continue going in n seconds, I will probably hit it. So you will take a corrective action to avoid collision, for example. The only difference between like normal driver logic and model predictive control is that the controller actually takes into account all of the states leading up to that point ahead of time. So one might see clearly why the bigger the prediction horizon and the bigger the dimensions of the system, well, the bigger the computational load will be, which poses quite a problem for real-time applications. And here is where we arrive at our objective, which is to propose strategies to apply model predictive control to embedded systems, specifically to holonomic robotic bases. First, let's talk about which types of systems we can have. And for simplicity's sake, we'll define convex systems as those that have one global minimum instead of having a local minimum, for example. And for this, you can usually apply linear model predictive control solvers like these ones. However, when you have a local minimum, you have to use a different type of strategy because these ones cannot distinguish between local or global. Like these ones, sequential quadratic programming and learning-based methods. Now, unfortunately, in robotics, you usually have lots of rotation matrices. So you have to use a nonlinear model predictive control if you want to find actually the global minimum for these types of systems. However, for holonomic robots, if what you truly care about is only the position and the computation time, you might make some considerations that will allow you to use first order methods. Which one? Well, we selected approximal gradients method. So you have your cost function, for example, composed of a convex smooth part and maybe a non-smooth component. And the proximal operator works basically by receiving an initial guess and evaluating or basically finding a balance between the value on this non-smooth function and staying near that initial guess, which can be a bit abstract. But when the non-smooth function is the indicator function, because it is an optimization problem, it basically throws out any options that are outside of the feasible set, making this proximal operator a projection. And now, for the final part of this method, to actually achieve or get close to the minimum, you will actually apply a gradient step, which depends on a constant that you will define. And of course, this way you can ensure you will eventually arrive there. In a practical example, it might look something like this, where let's say in an iteration you have your optimal set of inputs, and in the next iteration, if you attempt to evaluate the same inputs, well, you might not have the global minimum, the same global minimum. So you have to apply the method to get close to the minimum once again. Now you have to be careful because if your gradient step is too big, well, you can basically diverge and never arrive to the global minimum, which is why it is normally defined with these functions, where the Hessian or H is the Hessian of the cost function of your optimization problem. Now let's talk about the model of the robot itself. We chose a mechanism wheel base, which is basically because this is a very well-known type of robot, where we all know that the robots are the ones responsible for the holonomic movement, and your model might look something like this. We have your state variables, the relationship between the wheel frames and the robot frame, your inertia matrices, rotation and linear, and your system. Now, please note that the nonlinearity stems from the rotation matrices, but we will handle it a bit soon. Let's rewrite the system for a state space representation like so, where we consider the inputs being directly the torques of the motors and the states being the position on X and Y and the angle, and of course the derivatives of this. So there we have 6 states. For notation purposes, we'll use I and O, referring to identity and zero matrices like so. Now, once again, considering that you only really care about the position of your holonomic robot base, and you really do not care what's the orientation of the robot, well, you might want to constrain the rotation movement of this like so, which would have the effect on the system by making it more compact and easier for the optimization problem. For example, restraining this state will have the immediate effect in the state matrix like so. Now, please note that the rotation matrix is still considered, but instead of depending on a state, it will depend on the initial angle of the robot before beginning its movement. So, for example, if the initial angle is 0, well, the rotation matrix is actually an identity matrix. Now, of course, since now we're not considering the rotation, well, our model can be more compact, considering only the position in X and Y and its velocities, reducing the amount of states that we actually have to consider for the optimization problem. Now, the next consideration we will actually make stems from basically how the model was defined. Because the wheels were enumerated in this order, we have this relationship between the wheels and the base frame. But if we notice something, we can rearrange the order in which we number the wheels and basically arrive at a conclusion that this is the same matrix twice, but concatenated to itself. So basically, we have the same system twice in a single system. And what this means is that we can group the diagonal pairs of wheels to actually reduce the amount of inputs we actually have to compute. Why? Because it is not necessary to compute the same thing twice. And of course, this would be the result of the model. Now, instead of lastly, for the last consideration itself, instead of using a single huge model predictive control for this all of these or all of the states and inputs, we can actually use a cascaded control scheme where the PID controller, common controller, handles the actual basically feeding the set points to the motors, and the model predictive control can focus on the position and the odometry of the robot. Of course, they will have the effect of reducing the amount of time that you would have to spend on each iteration to actually compute the inputs. So now that we have our continuous model, we can actually start to define the model predictive control by first transforming it to a discrete model with an approximation method, for example. And first we have to, of course, extrapolate this discrete model. Instead of the next state, we say the next 2 states, or how would it look like? And of course, we can notice that we already know what's the representation of this next state. And we can extrapolate this logic to basically obtain a formula that computes the future state in a point in the future, basically depending on the set of inputs that you will input to the system. And of course, if we know a formula to obtain any state in the future, we can extrapolate that to a formula to obtain all of the states in the future based on a set of inputs that you will input to the system. And the final model will look something like this. However, these matrices are actually quite big, which is why we made so many considerations to basically minimize the load that will actually go into the optimization problem. So with this, we can actually begin to define the optimization problem, which usually looks like this, because it has to be convex to actually use the proposed method. So our cost function will look something like this, where the first thing of note is that the C set point is the vector set point where we actually want our robot to go. The first cost is the difference between the actual position and where the robot actually wants to go, so that at the end you actually arrive to the goal. And the second cost is the magnitude of the input. So at the end of the motion, you basically zero all of your motor accelerations. And the last cost is the difference between one input and another, so that you have a more smooth motion of your robot. Now, please note that each of these costs has a weight to it. So by changing it, we will be able to change the behavior of the system. For example, we have to be careful by not making the cost of the input magnitude too high, because otherwise the other cost will never overcome that cost, and your robot would basically not move at all. Now, we actually have to expand this cost function and to reduce it once again to achieve the quadratic form. And basically your matrices will look something like this. The Hessian matrix of the normal cost function, and the other one it will look something like this. And now with this, we have the normal model predictive control. If we actually want to employ our proposed method, we actually have to make some further considerations. Here are the formulas we're going to use. Basically, we have to compute what the gradient would be, and we have to remember the projected operator from distance from the proximal operator. And once again, if we expand the terms and rearrange it to have a quadratic form, we have these matrices. Now, please remember that the gradient step actually depends on the maximum eigenvalue of the Hessian matrix of the original cost function, because this one for the proximal gradient method is actually a huge identity matrix. This is where basically the minimized or the relaxation of the optimization problem stems from, where the huge square matrix actually is a huge one, basically. Now, lastly, we have to consider the obstacle avoidance for the robots. Normally, when you have a robot and you have an obstacle, you usually want to avoid collision. So you define basically keep out zones, like so. You can basically relate the origin frame of an obstacle and origin frame of a robot to actually change that keep out zone to something more like this. What we actually are going to use is a piecewise polynomial approximation that basically defines an equality constraint based on where the robot is with respect to the obstacle. So it might look something like this. Basically, you have many overlapped keep out zones, and the one that will apply will depend on where the robot is with respect to the obstacle. For example, if you're over here and you want to go over here, well, the actual keep out zone would be the one in this quadrant rather than the one you're actually on. And once you move away from or once you actually move from quadrant to quadrant, then the next or the inequality constraint will switch up. Here is basically the whole integrated diagram of all of the individual elements together, where the model predictive control here refers both to the normal one or to the one with the proximal gradient. And of course, with this, we can now make our experiments. First, we'll make one without obstacles to basically ensure that the effect of applying the proximal gradient method is actually positive on the computational time. And we actually can see that, we basically put timers on the code to measure how much time it took. We can see they both achieved the same convergence to the same point, and however the proposed method is a bit faster. With this proof, we can move on to the next experiment, where we actually apply the obstacle avoidance And once again, we measure the time spent by each of the methods, the normal one and the proximal gradient one. And we can clearly see that the proposed method is still faster than the normal one. And once again, they both competently avoid the obstacles and arrive to the designated goal. For future works, of course, we could take this algorithm, take this control strategy and implement it to a real robot to actually validate that it works in real-time applications. And additionally, we could also compare it to one of the mentioned nonlinear methods, which are, for example, sequential quadratic programming, much more computationally expensive to actually see what was the main benefit of having such considerations, at least for real-time applications. Thank you so much for your attentions, and I look forward to your questions.
For the presentation. So do you have any questions? Yeah, there's a question online. Please, Hector Atel, if you can make your question, please. If you can turn on your camera. He raised.
I think it was a reaction rather than a. Oh, it was a question.
Can you turn on your mic?
Yes, thank you. In your presentation, you say that in order to reduce the computational needs, you reflect your wheels, the effective your wheels.
Mm-hmm.
So that implies that your wheels are going to work in pairs always, or there is a way that you can control the input of every wheel separately?
Well, actually, for if you're only concerned, remember, if you fix the angle motion or the angle change, you would not have the need to control them separately. They will still be controlled separately in the PID to actually ensure that the set points that arrive to the or that are outputted by the MPC are followed. But there's no need to control them individually in other place that other than the PID.
Okay, thank you.
Yes.
Okay. Okay. Well, if there's any question, we'd like to thank the speaker, and well, thank you very much for your presentation.
Thank you so much for your time.
So we will continue with the next talk. The speaker is Saul Cordova. If you can turn on your mic, your camera and mic, please. Yeah. So I did see. Oh, okay. Then the presentation will be in the room.
Yeah.
So we'll start putting his presentation on screen, please. So the next talk will be adaptive PD controller on a PDTOL based system based on a single neural network. And go ahead, please.
Okay, thank you. Good afternoon, everyone. My name is Saul Cordova. I'm a bionic engineer student here in Instituto Politécnico Nacional. And with my colleagues, the doctors Alejandro Villaseñor and Octavio Gutierrez, will be presenting to you the paper entitled Adaptive PD Controller based on a pivotal system based on a single neural network. Next one, please. First, I would like to start by introducing the system it was worked with. The PPTOL, or planar vertical takeoff and landing system, is widely used as a benchmark model in nonlinear control because it exhibits two challenging properties. The first one is a strong coupling between the state variables, which means that when you change one input variable, such as thrust, it directly affects more than one state variable at the same time, for example, the height and the horizontal position. The second one is non-minimum phase behavior. In other words, when you try to minimize the error in one of the state variables, the error initially increases in another one. On the right side of the slide, we have the diagram of the PBTOL aircraft system, where F1 and F2 represents the forces generated by the propellers. The addition of them defines U1, that is the thrust, and the difference between them defines U2, which is the rolling moment. The problem that was tried to solve is the trajectory tracking under external disturbances such as wind, because we know those are some of the limitations of classical controllers such as PID or the LQR. We have to remember that both of them have constant gains. The next one, please. Sorry. Well, that's why it was proposed an adaptive PD controller using a single neural network. It will present online weight update and won't need prior training. One of the hypotheses is that it will exhibit robustness against external disturbances. And finally, it was compared with LQR using the ITIE index. No.
Next one.
Yes, thank you. So it was worked with a normalized dynamical equation of the PBTO, meaning that the gravity and the weights were set to 1. In the equations number 1 and number 2, there is a coupling term represented by the letter epsilon and represents the coupling between the vertical thrust and the rolling moment. And in the angular acceleration, it was added a term AL, which models the air disturbance. For the air velocity, it was proposed a cosine signal with random parameters. Okay. So for the control scheme, before we go to the comparison between both controllers, first I would like to explain each of them by its own. For the classical PD controller, we have the reference minus the actual position that is being multiplied by a proportional gain, and we add and then we have the derivative gain plus times the derivative of the error in respect of time. For the single neural network, we have n entries, which are represented by the letter x. Then each of them is being multiplied by a gain that it's called synaptic weights and are represented by the letter w. Then we have the bias that will help us to polarize our neuron. All of that goes to a sum block, and the output of that goes to an activation function. It was proposed a hyperbolic tangent because it exhibits a soft change between the negative numbers and the positive ones. Then in the classic neural network, thanks. For the error in neural networks is the target minus the actual output of the neuron. In this case, it was proposed that the entries of the neuron were the errors of the system, and the target is always to get them closer to 0. That's why we can simplify the expression and just write the error equals minus the entries. It was added a relevance error matrix represented by the letter capital E. And for the bias and weight update, it is important to say that there is an alpha term which represents the learning rate that will define how quick the neuron learns. So for the comparison, in the state feedback, we have 2 entries and 2 constant gains. And for the neural network, we have 2 entries and 2 adaptive weights and the bias. The bias in this case will act as an adaptive correction factor for the error in the steady state. The next one, please. Yes, for the height horizontal attitude control. So in order to get the theta reference from the x reference, it was supposed an ideal system and a constant height, and it was solved for theta 1. We divided the system into 2 subsystems. The first one is the high system control, and the second one is the horizontal attitude system control. The next one, please. Well, here are the parameters that were used in the simulations. We can observe in chart 2 that the learning rate was higher, as 4 weights are required to be trained instead of 2. And for the relevance matrix in chart 1, we have that it gives the same importance to all the entries. And for the in chart 2, we can see that the relevance matrix gives more importance to the acceleration in the x-axis. And all the initial conditions were set to 0 at the start. The next one, please. Yes, so here, based on the parameters in the previous charts, the trajectories. The results are shown in blue for the reference, black for the LQR, and in orange for the proposal. We can observe in the figure 2 that when there's a change in the acceleration, the LQR deviates more from the tracking for the desired trajectory, and the proposal tries to adapt itself to keep the trajectory tracking accurately. For the Y state, we can observe that due to the training time, the proposal deviates from the desired trajectory, but after the training time, it keeps tracking the trajectory accurately. And when there is a change in the acceleration again, the LQR presents some deviations from the desired trajectory. The next one, please. For tracking trajectory error, in the x-axis, we can observe that the range in the error oscillation is lower than in the LQR. And in the y-axis, the proposal presents a higher amplitude error oscillations before it is trained, but after the 10th second, the error gets closer to 0. There is where the bias term acts, minimizing the error in the steady state and avoiding those oscillations that presents the LQR. Now the next one, please. For the control inputs, the energy usage in the control input U2 are due to the training time, but we can also observe when there is a change in the acceleration, the proposal tried to adapt its weight using energy to keep the trajectory tracking accurately. And and in U1, there is a higher energy usage again, but due to the training time. And after the training time, we can see that the energy usage in the proposal is lower than in the LQR. The next one, please. So, according to the ITIE index results, we can conclude that the proposal reaches the steady state quicker than the LQR. And as we can see in chart number 4, and in chart number 5, the ITIE index represents the energy usage. We have to keep in mind that the proposal uses energy to adapt and train itself in real time, in online. The next one, please. So, what are the conclusions? The improvement in the tracking trajectory is confirmed by the ITIE index performance index showing lower trajectory errors. However, the adaptive PD controller required higher control effort, mainly due to the initial training time of the neural network. And the study shows that even a very simple neural structure, one neuron, can implement an adaptive control system robust to external disturbances. Next. Okay, so for future and perspective, we can apply to another system such as double pendulum or Purza pendulum, etc. And the formal stability proof of the proposed controller using Lyapunov-based methods. Here is the bibliography, and thanks for your attention.
Okay, thank you very much for your presentation. So I don't know if is there any questions you want to ask?
Yes, I have a question. In the control inputs, live with the control input, are the control inputs bounded after in the results? There,
The 10th, I think, the other
a
one.
slide before. That's like at the beginning, which I watch oscillations.
Yes.
these oscillations maybe are dangerous for a real-time input control.
Yes.
Okay, that these control input, well, there, those control inputs are bounded. So after this value, the control input do not increase.
Yes. For the tangent hyperbolic, the classical hyperbolic tangent is bounded to -1 to 1. In this case, it was bounded with -2 and 2. So yes, they are bounded. Or
You say hyperbolic tangent. Do you use that function to bound the control, control inputs?
yes, because can we go back to the other one? Another one? Another one? Another one? There. Yes, the activation function for the neural networks acts like a bounding system. For example, when you use a pure line, the output of the zoom block goes directly to the output. But in this case, as we are using the hyperbolic tangent, it only can take values from -2 to +2.
Why to use hyperbolic tangent instead of a classic saturation function, a linear saturation function?
Well, in this case, we tried another ones, but this one were the one that gives better results.
Its function was better.
Yes.
Thank you.
Okay, thank you very much for the question. Now I have a question. How can we see the results with the controllers? Is that next one? That one.
Yes.
For a real system, that would be, it's kind of strange that it works because we're in the seconds, 0.5 seconds. And like the input 1, it stays at 0, and the other one is just oscillating. So that thing would turn. How can you assure that it's stable? I know it's simulation, but how realistic is that? Because that, I mean, in that time from before 4 or 3 seconds, wouldn't that be unstable?
Just in the first seconds, I think, but those could be some of the future works. Here, the weights were initialized to random values, but we can use a different weight initialization like Xavier or transfer learning to minimize the training time and to avoid those oscillations in the training time.
Okay. And did you study stability?
Sorry,
Well, the stability of the systems, how can it's stable? Because that doesn't seem stable, at least in the control inputs.
I mean, to prove the stability, we have to first prove it by some Lyapunov methods.
Okay.
But in this case, if we go to yes, I know that the control inputs were oscillating at the first time due to a training time, and after that, it's just adapting itself to the air disturbances. But in the tracking trajectory, if we can go back, I think it seems more stable than in the training time. So after the training time, I don't know if we can say that it is stable, but it gets closer to the LQR system, which is an stable control system.
Yeah, but maybe make a switch there because it's, I mean, we had to have in the lab a PV tool, and it's not easy. And that it's really difficult to control. It's not really, and that so that you have to assure stability because if not, when you put that in the lab, it's really going to be difficult to in real systems. It could have a lot of difficulties.
one of the future works is to to get that in the real world, for example.
And how would you implement that in a real system? How would you go about putting a PDTOL for lab use?
Well, we have the input U1 and U2, and those are the entries of the system. So we can make a system equation and solve for F1 and F2, and those are the forces that are generated by the propeller.
Yeah, okay, so, but how would you construct a prototype?
Construct a prototype. Well, in this case, it's only a 2-dimensional system that only goes in X and Y. So maybe.
How would you measure X and Y?
Maybe with a laser sensor, a density, distance laser sensor, or maybe with a camera.
A camera. Yeah. And with the camera, how would you measure the angle? You need X, Y, and angle.
The angle. Well, if we put two, maybe two flashlights here, we can obtain. And if we assure that the camera is totally horizontal, we can obtain the angular position with the flashing lights, for example. I mean, it's a quick idea, but I think it's one of them.
Yeah, because the product we built, it was I don't know if you know the hockey tables, the air hockeys.
Yes.
It's a table with, you put air in, you have a bunch of holes, and we had a disc with 2 motors and an RC control for each motor, and with a camera, fixed camera, and that's one way to go. Because actually, just put it in the air, it's very difficult. So that you have a bed and just you can put it horizontal, or you can put perturbations, putting it up at an angle. That's one way to go.
Okay, thank you.
Well, thank you very much. Is there any other questions?
Yes.
I have one question regarding you put like the control of the height of the vehicle, and you control also the translational movement, no?
Yes.
But my question is that this translational movement is coupled by the role or the orientation of the vehicle body. And my question here is why you didn't put the because to follow a trajectory in this direction, you need to put a trajectory in the orientation. So you need a orientation desired and also a control in this to follow a trajectory in this y axis. So my question here is why you didn't put this.
Yes, can we go back please to slide number 4? No, sorry, those 6. Yes. Here, in order to control the horizontal position, we have an X reference trajectory, a desired trajectory. And in order to get a rolling moment, a desired rolling moment, we suppose an ideal system here from the X acceleration, and we can set the coupling term to 0. So we are just left with this part over here. And if we set a constant height, well, as we are working with the normal dynamical equations, the gravity and the weight are set to 1. So the 1 is the minimum force that we need to control the gravity. So the U1 term goes to 1, and if we solve for theta 1, we can obtain a theta reference, which is the angular position from the X reference.
But for example, in the graphs, could you please show us the graphs?
Oh, here now I understand. Okay.
For example, here between the 10 and the 30 second, the vehicle is at a constant height, but it's impossible to move in the y direction with a constant height. For example, imagine this: you are moving in this direction, but you cannot move with a constant height, because if the vehicle have an orientation, the vehicle will move, of course, in the height, of course, with an angle. So it's, I think, I don't know why only if you restrict the movement, but I don't think it's realistic this, because only imagine the movement of the vehicle. It's impossible only in the case that you have like a movement in a exactly this position. You can move in without changing your height, because to change your if you don't want to change your height, you need to be in this position. But this is not possible because the pivotal cannot make this, because you lost the degree of freedom, this degree of freedom. If you put you are moving in the zeta axis with two thrusters here, and if you put in this position, you cannot control the height anymore, because you lose this degree of freedom.
Sure.
So my question here is that I don't know how you make this impression.
Okay, the simulation, well, there are the parameters, but also for the x state, the error is not zero always. Can we go to the other one, please? The next one. There, the error is not always zero, so we are not restricting the movement. We didn't put the theta reference because, I mean, when you don't have a theta, you won't have a theta reference for literal. Well, you will have a theta reference for the trajectory, but it won't be general. So in this case, you only put the y and the x axis, but I have the theta reference, and it's not always going to be zero. In this case, from the I know that what you're meaning, that when you have the total horizontal position of the pivotal, you can control the thrust. But in this case, you can control the x movement and the y movement at the same time with the two propellers. We never put the pivotal system in a truly vertical position. I don't know if.
Yeah. Okay. No, don't worry about. This is my question. And the other question, I have a question. I don't have it. Yeah, if I have some time. But regarding your conclusion, you say that it's you conclude that it's robust against disturbances. But I don't know if you put a scenario with some disturbance. Or
Yes, all of them are in orbital disturbance. Can we please?
Okay.
Yeah, yes. Bueno, podría cortar si quieres para que ya funcione. Thank you. Sorry. Here for the simulations, no. Here, in the theta acceleration, the term AL models the air disturbance. In this case, the only one that is going to change along the time is the air velocity, and we proposed a quotient signal with random parameters. And here, the random parameters are the one that have ranges, and if we if we increase those ranges, the air disturbance is going to be higher.
Yes. Okay.
Thank you. No, thanks to you.
Okay, well, if there's any questions, well, thank you very much. And well, this will be the final talk of this session. So thank you very much, everybody, for coming, and we will be closing this session. Thanks.
Thanks.
Thank you.